All righty, so let's go ahead. I just started the live stream, and let's pick up where we left off last time. We were talking about magnetic torques, and what I want to do is maybe look at a problem and see. Let me get these people added in here, and let's try and maybe just see if you remember some stuff from last time before we just blow past it. Okay, so let me start with the screen share. Oh, I lost it. There we go. Ah, oh, the good old days. Moving drones. Nope, that's not what you're doing. Let's get into here. There we go. So let's say we have a loop. Um, I want to point out something on this problem here. I forgot to write the mass in problem 28.17. So assume that mass is given, okay? Sorry about that. And then why don't we, I'm going to leave 28.17 for you to try at home or maybe later today if we want. Let's skip ahead to 28.18 and see where this one goes. And so let me scroll down there. Again, so add in, and this is on page 146. So if you're wondering where we're at in the workbook, page 146, make sure you add in M as a given. Otherwise, that problem is pretty tough to solve. All right, and then let's clear that out. So let's focus on this one down here. There we go. Long piece of wire, mass M, total length L. You're going to make a rectangular coil with sides H and W. HW. The coil is hinged along the horizontal side. Okay, so the hinge is up there at the top, and the coil carries some current, capital I. We're going to put this in an external magnetic field that's constant, uniform, vertical. Got it. Somewhere on the hinge is a battery. Okay, got it. So somehow this is a physically possible thing. You can imagine having a loop of wire and you put a battery on the hinge, and it's so this is the idea that I wanted to talk about right here. We've got this external field here. Okay. And the idea is when you turn on the external field, when you give this thing a B external, B external, bejext. When you turn on the external field, the loop turns. This is totally plausible. Now, clearly, we know that the loop rotated this way. So now, according to this coordinate system here, and I'm going to get rid of that external just so it's not so confusing with the bejext. According to this coordinate system, what direction is the magnetic torque?
I-hat?
Nope. Remember, torque does not point in the direction it twists. It points in the direction of the axis. And so you want to say I-hat because that's the way it moves. But that's not correct in terms of the torque equation. So whoops. So think again there. Let me find my eraser.
Yeah, K-hat then, right?
I think so. Yes, I agree. K-hat. So the torque is in the K-hat. And actually, instead of calling it torque, let's call it torque hat. So if I call it torque hat, that means the direction of torque. I hope that makes sense to you. So the direction of torque is K hat, which in this case is a dot. All right. All right. So which way is the gravitational torque, if you had to guess? When this loop lifts up, which way does gravity make it twist?
Negative K hat?
That's right. So we know that the torque due to B is twisting it that way. you could think about the gravitational force is trying to twist it the other way. So that's the torque due to mg. And so that would be in the other direction, which would be negative k hat. Again, we don't think of torques as being clockwise or counterclockwise so much as being in the k hat or negative k hat, meaning the axis is in the negative k hat, or the axis if you use your right hand. All right. I'm going to go ahead and get this drawn up on the board just so we could talk about it more, but that gets you a start on this question. So you go ahead and think about it while I get it drawn up. Okay. Okay. Okay, here we go. We know that there's going to be a magnetic torque this way. We know that there's going to be a gravitational torque this way. All right. And let's see here. So torque again is the x. So this one is going to end up being, I think we said positive k hat, because the axis is, and this one is going to be negative k hat. All right. There we go. All right. Sorry for that glare there. All right. And our goal in part A is, which direction is the current flowing? Well, we know that the magnetic field is in here, pointing this way. Any thoughts on how we could figure this out? That's B external. Notice that's J hat. What are we trying to do? What direction is current running at the bottom of the loop in the far right picture? So this way. It's either into or out of the page, right? Because at the bottom, so we're looking at a side view of this loop. So the loop, yeah.
Negative k hat?
I think so, but let's find out. So again, just to be clear, imagine this book is the loop. So the loop is like the edge running around and around and around here, right? So the idea is we're looking at this loop like this. And so at the bottom, current's either got to flow into the page or out of the page. So that's the loop, if that helps you kind of visualize this. From the front, it would look like this, and you can't really tell if it's angled or not. That's why, right? Because it's really hard to see. So that's why I'm drawing this way, so we could see that angle. Trey suggested into the page. So let's check. So the idea here is he suggests current is into the page at the bottom. So let's see. I have no idea. So he's saying, is this I? That's our question. How do we check? Well, I guess, what's your thought process there, Trey?
The right hand rule.
Which one? What equation were you using to get your right hand rule?
Oh man, so many right hand rules.
Yeah. Was it a force or a torque?
The force. The force.
Okay, so Trey went this way. He said force equals I L cross B. So he's thinking there needs to be a force that way. Is that what you were thinking?
Yes.
Okay, so let's see if that's right. I Okay, remember that L points in the same direction as I. So in this case, I goes to B, gives me a force that way, which would make sense with the torque this way. I agree with that. Any questions about that? Remember, this is one way to get a right-hand rule. First vector goes to second vector goes to output. Input 1 goes to input 2, output. Okay, that's good. I was not thinking that way. Somebody else, what's the torque equation? Does anybody remember the torque equation?
Mu cross B external.
What direction is mu? I might as well color this while you're thinking. What direction is mu? Do you remember the right-hand rule for figuring out direction of mu?
The direction of the area vector, right?
Yeah. So where there's two possible directions for the area vector. Again, this is our loop, right? Which way does the area vector point relative to the plane of the area? Does it point in the plane or perpendicular to it?
Perpendicular to the right and out.
Yeah. So it's either going to be this way or that way. All right. Like that. So it's either going to be this way or that way. All right. In this case, it's either going to be that way or this way. How do you figure out which one it is? Curl your fingers in the direction of what?
The current.
Yeah. So if it's going into the page here, wouldn't it be going down the page this way? Let's see. Mu points this way, right? Girls. Oh, mercy. All right, so that's the direction of mu. Now let's think conceptually here. If mu is pointed this way, do you remember anything about what mu likes to do relative to the external field? Does it want to align with it or does it want to anti-align with it? Remember, mu is like the magnetic field associated with this loop in a sense, or it relates to it anyways. Do magnets like to be aligned or anti-aligned?
Would it be aligned?
Yeah. And do you see what's happening here? Initially, the loop was hanging straight down and mu was this way. It's trying to align itself. Do you see that? So I know that seems weird. And this one, you're probably like, that understood. If this works for you, great. But I'd like you to also get this extra intuition, especially you chemists out there, right? So if you have to do magnetism in chemistry, you usually know magnetic moments of molecules, not current, right? So there's a reason to know this. If you want to understand modern physics, this will help you. So that's kind of cool. So it starts here and then it's trying to snap there, but it can't. All right, so that's pretty good. And then as a last one,
so could I ask something really quick? So you're saying that it's it's trying to line up with the magnetic field, you're saying?
The external magnetic field, yes.
The B external.
Yes.
Okay. So it's starting at that vertical point and then it's flipping.
Exactly.
So it would be
you put it here and then you turn on the external magnetic field, say by bringing the magnet close.
Yeah.
And when you do that, it goes, whoa, hello. And in practice, it's going to do something like this, right? It's going to overshoot and kind of balance out and settle in. So it's going to go,
okay.
whoa, 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 whoa.
Sweet. Thank you.
Cool. Yeah. All right. I better read the question and find out what the heck we're trying to do here. Let's see what we're doing. Ooh, part B. We're supposed to get the number of turns. We were told that it has length. Actually, let's just screen share for a second. That's not going to go anywhere. We can get right back to that. We're supposed to now, okay, so that's this. I agree. Both of those things confirmed. Trace was the easiest in this case. The other one is sometimes easier in other cases. So that's why we're doing both. Next. Whoa. Any thoughts? We have a piece of wire and it's got total length L, and we're going to turn it into this rectangular coil. How do I get the number of turns? Somebody.
Would it be L divided by 2W plus 2H?
I like it. So the idea is the length divided by the perimeter equals the number of turns, right? And so if you had a circular loop, you'd have length divided by 2 pi r. In this case, the perimeter was 2 times the width plus 2 times the height. Now let's check. What are the units for a number of turns?
Unitless.
Unitless, meters over meters. Yeah. Oh, yeah. Okay. So that's part B. Nice. Every once in a while that'll show up on a quiz question or something, but I don't know. Okay, next. Let's get that magnetic moment. All right. So does anybody remember the magnetic moment? The equation, it's written on your equation sheet on the back. It was something like N, I, area vector. I think we have all the pieces here. So help me out. N was, that's the number of turns. I is I. What's the area vector?
Is that when it's in its starting position, or does it not matter?
Oh, I guess I'm assuming in this position. Sorry. I should make that more clear. Let me see what I said in here. Yeah, that's absolutely not clear, but it should be for the last picture. So let me put a note in here to myself. Was that 146? Yep. Okay, so that said, was that you, Tom?
Yeah.
Okay, so what do you think the area vector is in this final state?
You know the angle, so it would be
We're told that this thing here is theta, right?
yeah.
Okay. Oh, I see. In the end, we're going to try and figure out theta. You're right. You're right. But so we may need to write it in terms of theta.
I think it's going to be cosine theta j hat plus sine theta I hat.
Okay, so let me think. You're saying if this is theta, what's this angle right here, Tom? Just so I could follow. I don't know if you're right.
That'll be theta as well, right?
So how about this angle?
90 plus theta.
If this is theta, this is the other half of that. So that's
minus theta.
So that means this angle down here is probably theta, right? Because he said this is theta. So this is 90 minus theta, I think. And so you said, and so what did you say in the I hat and J hat again? Sorry, I lost it.
I think it was cosine j hat plus sine I hat.
And then
Sure.
based off this, what do you think it should be? Which term gets the I hat, or which term gets the cosine?
Cosine would be the I hat in that, right?
Yeah, exactly. So is it going to be positive or negative in the I hat and J hat for this one?
I'm thinking positive in both.
I agree.
First quadrant.
Yep. All right. So is that it? And anybody can chime in. Tom, you're off the hook. I appreciate you participating there. That was good. What do you think? Is that everything, or are we good to go?
Area vector of HW then?
Exactly. So this is the direction. So that's actually area hat. That's the direction it points. Don't forget to throw in HW. And Tom may have said that, and I probably glossed over it, but just making sure. So notice this now has the correct units. No units, no units. Current, that's current. And this has units of meters squared. And this is the direction. So now we've got the mu. All right. Next. What's the next part say? Oh, let's just screen share. Determine the angle, equilibrium. All right. When you hear that sentence, what does that make you think?
Forces.
Say again. Sorry, it cut out.
Forces or torques canceling?
Yeah, so forces is usually the first thing, but don't forget, we also have torques balance here. Now, if you try and do the forces balancing, we're going to run into trouble. Why is this going to be difficult if we try and analyze the forces? Let's go back to our picture on the board, right? We've got the weight force is going to be pulling straight down. I know that there's this, we could try and figure out the magnetic force. What else? Are there any other forces? How about we draw the forces? Okay.
There friction in the hinge or something?
Yep, the hinge.
The hinge. There's going to be an mg straight down. There's going to be a force magnetic this way. And the hinge is going to push which way?
Up and to the right?
Up, and to balance this, it has
Right
to be,
left.
yeah.
Left.
So there's going to be a hinge force this way, an Rx and an Ry. Now, the thing that I would probably do, sort of like Nick was saying, the default is just point this one up and that one to the right. And then if you get a negative answer, you're like, okay, I guess it was to the left, right? So either way would have worked. So you could call this reaction X and reaction Y. Do we know reaction X or reaction Y in this case? Do you know numbers for those like right now?
No.
No. And so this would definitely get the angles involved. However, it's not, we don't know what these are, so we aren't going to be able to solve. This is a good idea to try. And when I'd start doing this one, I'd quickly find out, this isn't going to help me find theta, even though it may have originally looked like that. So that was a great idea to try forces. And then, as Tom said, the other option would be for equilibrium of torques. So I think it's pretty obvious which one that's going to be based on the fact that I spent a lot of time on torques here. So let's go ahead and rock it. Nice job, everybody. Nice job. So I need some space. And so I'm going to, oh, whoops. This is wrong a little bit because I forgot the arrow right there, right? Sorry about that. All right. So I'm going to go ahead and write this all down. So I know that the torque the sum of torque vectors equals 0. That says the torque due to mg plus the torque due to the magnetic field external should equal 0. Now, we could actually take this one step further and get rid of these by saying the torque magnitude due to mg in the negative k hat plus the torque magnitude due to b in the positive k hat is equal to 0. Or you could skip right to this step. The torque magnitudes have to be equal because there's only 2 of them. Now, in general, this is the way you get to that, but I hope you agree you probably could have just jumped right to there in this special case. Well, we know they're going opposite ways, so their magnitudes must balance. Does everybody understand the subtle difference between they add to 0 and they equal each other? I hope so. Right? They add together to 0 as vectors. They equal each other in magnitude. All right, so there's that. Let's go ahead and rock this out. And let's just use this last, well, I guess we better figure these out, right? So let's try to figure out, oh my gosh, I just wish I had more board space. So I'll just write this again up here. So we could use either one of these two results. Either the magnitudes are equal or the torque vectors sum to 0. Let's figure out that torque due to B. Actually, we know it's mu cross B external. Since I only need the magnitude, what's another way to write this? How do I get the magnitude?
Torque equals mu times B without the vectors involved.
It's mu B
Sine theta.
sine of angle between. Watch out. Does everybody agree when I say it that way? Anytime you have a cross product, it's magnitude of the first, magnitude of the second, times sine of the angle between gets you this. Remind me, what's the angle between?
90 minus theta.
Aha! It's not theta in this case. Do you agree? Ah! In this particular case, it's 90 minus theta. Ah! So what's sine of 90 minus theta equal to?
That's cosine of theta.
Chapter 12. Don't you love it? Every chapter in physics gets reused just when you thought you could forget about it. Usually approximately after you just forgot about it, right? Oh, we never have to do torque again, right? Ha 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 ha. Sucks to be you. All right, there we go. Let's keep rocking. And at this point, what's the torque due to mg? Well, if I want to understand the torque due to mg, maybe I should get that picture back up here, right? Give me a second here. Okay, so here's my loop. Where does mg act on the loop?
On the center.
On the center. Okay. This angle's theta. Whoops. This angle's theta. So this, I think this angle's theta, right? Double check. We're told that this angle was theta. So isn't this angle theta?
Yeah.
How do I get torque due to magnetic field then? I mean, not magnetic field, torque due to mg. I'm sorry.
Be R cross F.
R cross F. I like that. Right? Well, now, actually, I only need the magnitude of that, right? Let's keep things simple if we can. What is R? What does that mean in this case? From what to what?
From the hinge to halfway down is half H.
Yeah. H over 2 that way is this R vector. Force is mg. So now, if I just want the magnitude, what's that going to be?
Is it just 1/2 HMG times sine of the angle between?
Which in this case,
sine
what's the
theta?
angle between? Yeah.
Yeah.
Now, you could also figure this out and write it as a vector, and you could figure this out, and that would just be mg negative j hat, but it takes a little bit more work, and so sometimes it's worth it to just say, well, this magnitude is h over 2, this magnitude is mg, sine of the angle between. Now, you might be saying, wait a minute, Jorsted, the angle is actually 180 minus theta, right? But I also know from trig, if you take these, if you punch in sine of 30 degrees and sine of 150 degrees, which is 180 minus 30, you get the same answer. There's a trig identity there, okay? So sine of theta equals sine of 180 minus theta. Either one of these angles works as the angle between for a torque. Is this bringing back PTSD from physics 1? I hope so.
I had a quick question about that. It doesn't work the same way with cosine, though, does it?
No.
Yeah. Okay.
So dot products, I don't know if you remember, Nick.
Yeah, it's
dot
AB cosine theta, right?
You'd get a minus sign if they were anti-parallel and a positive sign if they were parallel or parallel-ish.
Yeah.
Yeah. So with dot products, you actually had to worry about the sign of the output more. Whereas with cross products, we have to worry about the IJK crap. But the magnitude of the cross product is always going to be positive, and then we don't have to worry about that angle. All right, so at this point, the problem is basically solved. We know this magnitude, we know that magnitude. What are we looking for again? Angle. Set them equal, solve for theta. Let's just take a quick look at the solutions and see if there's anything worth noting that I've forgotten. $76 trombones. All right, so there we go. All right, a bunch of stuff, a bunch of words. All right, so here's where basically we just got to. We figured out these two, right? And that 90 minus theta was the trick. Most of the time you're like going cruising along, and somebody that didn't notice this would think the angle drops out because you'd have sine theta canceling. So now you get a tangent and you get some ugly mess. Did I forget a 2 somewhere? Oh no, the 2 drops out. Whoa, I didn't notice that at first. Isn't that kind of fun? So, all right, that's cool. All right. So this is a good review for torque. This is good for the civil engineers and mechanical engineers. Like, you guys actually have to know torques, and you call them moments and the difference, and that you can deal with that on your own. That's we don't really care about that here. All right. Let's try another one. Unless there's questions about this before we go on. Any questions on any of that crap? There you go. All right. Let's go ahead and take a look at another one. So these problems can get really sneaky because there's so many cross products, so many arrows, so many vectors, and that's actually a good thing for people to learn well, right? So, oh my gosh, I put this question on a test and it just destroyed people. 28.19. So, yeah, because people are not good with vectors conceptually. So 28.19 is a really good one for you to do at home. It's pretty conceptual. And 28.20, I'm telling you, this book is filled with problems people failed on my test. All right. So this was another one people failed miserably. Basically, this problem every year, I just put any random torque problem on and people fail in droves. So you should make sure you understand magnetic torques pretty well. I guess that's what I'm saying here, people. People are just bad at it. So do all of them and practice hard on these. That said, that it's fun too, in a way. How about we work through 28.19 as a team? Okay. This one, the words are so complicated in the solution, people get lost sometimes. I've rewritten the solution a couple different times. No matter how I rewrite it, people get confused. So I guess that means it's just a difficult concept. You got a triangular loop of wire. Okay, I'll draw it. Current is flowing that way. Okay. This side has length D. That side has length 3D. It's in the XY plane. Okay. It says, oh, current runs that way. Got it. We're able to place a hinge so that it may rotate. So we're trying to rotate this loop, and we could either put the hinge on the x-axis or the y-axis, and we're going to put it in an external magnetic field, and we can control that. Okay, so the first part says, let's put the axis on the x. Okay, so for part A, let's assume this is the axis, and now I know what to do. Okay. So in part A, we're going to put the axis on the x-axis, and we want this thing to turn or twist. We want a torque on it, right? So in this case, we want the torque to be, oh, we want no magnetic torque. All right. So help me out. That's a lot of words to digest. Any ideas how you might approach this problem? Any thoughts at all?
If we want no magnetic torque, then we want no magnetic force. We just put it parallel to the axis, right?
Okay, so all right. So Phil's thought is, what if we put B field this way? So I'm going to point out my strategy overall, which is related to Phil's here. Take a guess and try it, and then go from there. Otherwise, you just sit there staring at it forever and get nowhere. So why not try this, try that? This method is called trial and error. So why wouldn't you try all three of the principal axes? You see what I'm saying? Just try B, and just to keep it simple, let's just say B in the X, B in the Y, or B in the Z. Just try each one of them separately and see what happens. That's what I would recommend here, rather than trying to think. So let's start with what Phil said. He says, what if I put this here, right? So if I put the B field along the x-axis, is there going to be a torque? Well, let me see. What direction is the mu vector, Phil?
Sorry, into the page, I think?
Correct. Does everybody agree that that, whoops, is mu? And then what's the general equation for torque, Phil?
Mu times the...
Yep, mu cross B.
Yeah.
Yep, excellent. So based on what you just said, Phil, would this work? If you put in B to the right and mu is into the page, is torque equal to 0?
No, then, because we have... Yeah.
All right. And so I had no idea either, dude. So because these problems are so complicated, I actually sketched them out. So let's let somebody else try. Somebody else, how about B in the Y direction?
No.
Would that cause a torque?
Or yes, it would.
Okay. And so this, oh, and I guess, oh, we should be careful here. Wait, what did the question say? I want to read carefully. Did it say no torque or no torque about the x-axis? I forgot what it said.
This is
X-axis.
about x-axis.
Oh, shoot. Okay, so then I'm going to be careful. I want to do Phil's a little more thoroughly here. So, so if we put in an I hat here, and so actually Phil's is partially correct, right? So his does cause a torque, but not about the x-axis. So I was wrong there. I misspoke. So this is a negative k hat, right? Is this k hat or negative k hat? I goes to J goes to, so that's negative, right? Okay. So what direction is this torque? I got to think. So K goes to I goes to J. And since there's a negative K, it goes to, so this should be what? Negative J hat? So that would actually cause a torque about the y-axis. Yep. Nice job, Corey. Okay. All right. So Phil is correct that this doesn't do it. All right. So we're done, right? Or should we bother to check these? Do you think that one of these other ones would cause a torque that's not about the x-axis? What do you think?
Yes.
Probably, right? Yeah. And so let's take a look. If we use J hat, let's try that. So negative K hat crossed with, if B is in the J hat, what does that give us? Uh-oh. That's an I hat, right? That's a problem. K goes to J goes to negative I hat, but there's another negative, so it's positive I hat. So this one is a problem. Finally, let's check this one. If B is in the K hat, what's your torque?
0.
0. So what we see is if you want so the key word here was about the x-axis. The elbow method, hold your arms like, nice. Okay, so in this case, we see the B external could be, oh, shoot. Sorry. B external could be anything you want in the X, but it has to be 0 in the J hat, but then it could be anything you want in the K hat, right? Nah. And so let's go back and look at the answers now. Basically, we need 0 in the J hat, but anything else is fair game. So which of these answers best describes that?
The XZ plane.
I think so. Right? Because you could have a BX and a BZ. And so that's what I was trying to do with that. Oh, no. Look at the next one. All right, let's keep going. Part B. We switched from torque back to force. What do you think? Which orientation, I'm looking at part B now, which orientation of the uniform external magnetic field causes no net force on the loop? Any guesses? It's okay to guess and be wrong, right? This is class.
I mean, is the only other force that's working against though the like the force that's going in the negative k hat? Because
I see.
Torque, I guess.
Oh, actually, now I remember. I had to throw this question out on the test because of what you just said. You're thinking, oh, is there a weight force? All right. What I meant was no net magnetic force. And that reminds me. So when I say it that way, good job. You're reminding me of why I had to throw it out and then I forgot to update it. So no net magnetic force. Maybe I should just change that word to magnetic. Would that make more sense to you all? I'll fix that up. I'm going to write that down really quick. Hold on. So reword the question. No net magnetic force on the loop. Sorry about that. Yeah, I had to give all the students a free point for that on the paper test. Okay, what do you think? Any thoughts now? Basically, I want no magnetic force on the loop. Let's see, there's something in the chat. Anything is correct. Remember that we figured that out. We tried this with a couple of different problems. We did all those long integrals and then force was zero. Force was zero, whether you put it. So that's going to be true no matter what you do. A way to think about this is think about this loop. You essentially have a component this way and a component this way. If the B field is uniform, this component or this segment will cancel that component of the segment. This segment will cancel that component of the segment, no matter which way you put B field, because they're flipped, right? So any orientation will cancel that out. Nice job. All right. Ooh.
Could I ask a quick question on that? So, I mean, I remember you talked about like there being, when you said like if it's a closed loop, but so
closed loop and uniform external magnetic field. Those two things have to be true.
Okay, so
go ahead.
So the magnetic field, like how would I say, like you would just say that on a test, like you're gonna write that down if it wasn't a, you know, if it wasn't a circle a box question, like how would you would you just say because it's a closed?
You could say that a closed loop experiences no net force in a uniform external magnetic field, and underline the word uniform to stress it. Got it?
Yep.
But to be honest, these are ripe for multiple choice, right? It's an easy multiple choice to throw in some test question. If you look at my old test, it's on there about half the time as a multiple choice. All right, good question. All right, let's get to this one. Oh boy, this is getting gnarly now. Look at all these words. It's just so dense to read. Assume the external magnetic field initially causes maximal torque about the x-axis. Without reorienting the loop, the external magnetic field is reoriented to cause maximal torque about the y-axis. So, but the magnitude of the external magnetic field is unchanged. Which case gives bigger torque, right? So basically you have a magnet. This was very hard to read for people, I think. But the idea is you could put a magnet in here and you're either going to put it so it's lining up this way, or it could line up that way, or it could line up out of the page. And the question is, if you use the same magnet, are you going to get more torque about the x-axis or the y-axis? So again, let's say you have this scenario and you could line up the B field any way you want. Okay. And so you want to get the largest torque possible. Well, hopefully from this equation, you can tell you need a 90-degree angle between mu and B. Well, so this one's out. So you're either going to line up the B field to the X or line it up in the Y. And my question is, which one gives a bigger torque? Assuming you use the same size B field.
My guess is that they'd be equal if the B
Yeah,
field is
that's
the same
it.
size.
That's it. And so the magnetic moment really helps you see that. You're like, well, this isn't changing. If you try to do it with the torques and the forces on each segment of wire, you're going to spend all day. Whereas if you do it with magnetic moment, you're like, oh, the magnetic moment hasn't changed. The size of B hasn't changed. The angle between is 90 degrees in either case. This one gives me a torque about the Y. This one gives me a torque about the X. Oh, well, same torque magnitude. It just changes the axis. I don't know if that was fun or hell for you, but when students saw this during the test, I think that just freaked them out. So yeah. All right. But I guess what I'm trying to get at here is, boy, it's a lot easier to do a concept question when you write down an equation and kind of, maybe you don't do all the math, but having an equation on your page sitting there can sometimes help you kind of think it through and be like, oh yeah, this, that, see what changes. And obviously the picture helps.
Yeah, that
Questions?
definitely would help, because I was still thinking torque in the sense of like force times distance.
Yes.
So I thought, well, if it was about the y-axis, it'd be further out in x, so maybe it'd be have a higher torque. But no, just the fact that the magnitudes don't change completely solves that.
Exactly. And it saves a lot of calculation. All right, good job. Other questions on that? Anybody? Let's look at one more. And okay. Try this one. I'm going to get it drawn up as well. These questions are just they're simple if you see them, but you can only see them by practicing a lot and getting stung by like, oh, it's this. There's these tricks just add up at some point. You have an inclined plane built like this. Okay, I'm drawing it. I'll catch up in a minute. We'll look at it 28.20. Oh. Top face of the plane is the North Pole. Told we have a cylinder. N, we know I, we know the mass, and then we know X and theta. And I'll get to the chat here just a second here. Got it. Okay. And let me check the chat.
I'm a little confused. Why does it say height H? Is that into the page?
Aha. Well, the short answer is correct. How about I just say it that way? Do you agree that we must be looking at an end view of the cylinder? Agreed?
Correct.
Nice. So there's no shorter way to say that than you just got it correct. So if you could try and draw this and imagine it's going this way, right? And then this dimension right here would be what? What's that dimension?
2R?
2R. Yep. And I'll just put some shading on here so this looks kind of nice. Okay. So we can kind of tell that that shaded cylinder is supposed to be the same thing up there. Okay, good job. So let's go back, and we've got a bunch of crap given. We also know x and theta down here. All right, so let me go back to the picture and see what else we're supposed to figure out. Okay, give me a magnetic moment. Ooh, all right. I'm not going to tell you anything. You guys tell me what to do. Try to tell me without looking at the solutions if possible, but we're looking for we're supposed to be looking for mu. All right, so somebody tell me anything you know about mu. Anything. Get me rolling here.
We know it has n turns.
Got it. Oh, what's the equation for mu?
Oh, ni
A vector.
a vector.
Okay. So we know it has n, we know it has I. What's the area?
Pi r squared.
Nope. Pi r squared is this area. Is that the area of the loop?
2r times h.
That's the loop. Do you agree? Around the outside? So that is length times width.
Oh, I thought we were rotating like a coil.
It
didn't
is.
realize it was
It's a
around the outside.
rectangular coil, right?
Not like
so
a spring.
if this was a sphere or something, you'd be pi r squared and you'd be golden. So, all right. So is this correct?
There's no direction in there.
Aha. So what's the direction?
Which way is the current flowing?
I don't know. I didn't tell you. Let's see. What do we know? Ah, okay. Let's go back to the wording of the problem. You can see this gets nasty, right? Okay. What do we know here? Okay, so there was a key problem that we just addressed. We don't know the direction of the current. Nothing tells us that, does it? So I think that was Tom. Tom, can you give me some options? What are the possible directions of the magnetic moment?
We're either going to go plus or minus I hat.
Yeah, it's either this way or that way, right? Because it's got to be perpendicular to the loop. So that's good. What information in here helps us figure out which direction it points?
It remains at rest after release.
It remains at rest after release. Why does that help?
Does that mean the force is up the plane?
Let's try and talk torque. So you agree there's got to be some sort of force pushing it up the plane. Okay, fine. Give me a torque. What direction is the torque then?
Z hat?
Negative.
Negative k hat.
I got
K-hat.
it. It's some kind of either k hat or negative k hat, right? So what do? If we have this loop of wire, we want it to twist up. We want it to roll up, right? Oh shit, I'm not screen sharing. Sorry, hold on. So we want this thing to roll up the hill. So my axis needs to be into the page. Otherwise it won't roll up. So I know that does that sentence make sense? The direction of the magnetic torque is into the page, which means it rolls uphill. Well, how does that help?
So I get that the cross product of what is it, mu and b?
So you're doing the torque due to B is equal to something cross B. Okay. You said mu cross B external. B external.
Which is
All right.
equal to negative k hat.
Okay, so the output of this is going to have to be in the negative k hat. Well, so I know this is negative k hat. I know this is either plus or minus I hat, right? And our question is which one? That's what we're trying to figure out. Do we know which way B external points?
Up. Positive J hat.
It's not J hat, but you're close, Nick.
There's an angle in there.
It points out of north and into south. So B external is pointing this way. He got the idea, right? So, crap. Now, he was saying upwards, so we know there's a J hat component, but there's also an I hat component as well. Oh, do we have to worry about the I hat component and the J hat component both?
No, because I had
No,
just going
only
to
this.
cancel out.
Yeah. The I hat part's going to drop out, so let's just worry about the J hat part. Trial and error. Try both and tell me which one works.
Negative I hat.
I have no idea. Let me think. Okay, so there's a claim it's negative I hat. So I goes to J goes to K. So yep, that's it. So now that is the answer for this. This is why magnetism is fun. How much math did you have to do here? Basically none. It's all just, I just love it. It's like a delicious treat. Yeah, exactly. And so it's all about that cross product. All right. I have no idea what we're supposed to do. Let's reread. I'm just having fun with this problem because I enjoy it. Hey, we did it. We actually got part A. Okay, part B. Yay. Any idea what to do next? Part B.
And similar to the last one, where the torque from gravity matches the torque from the force or magnetic field.
So in this case, we know that torque due to magnetism is going this way. There's a torque this way. Okay. So in this case, if these two balance out, we get this thing to stay at rest. You could argue as well. You could say, well, what about a frictional force down here at the base? And that's a good claim. But I guess we're going to assume that frictional torque is negligible, which it usually is compared to a large magnetic torque. So I am ignoring a little bit. Usually the weight here and this would make the friction negligible probably. So there's a little bit of glossing over there. But yeah, anyways, more. Let's go ahead and so what would you do next then? Might as well get that magnetic torque while it's sitting right there, right? Oh, now I do. Oh, we better figure this out, right? Well, I guess, yeah, there's no good way. What you could do is we actually figured out the mu is pointing this way, right? Mu points this way. B points this way. This is theta. Iota theta. What's this one? Theta or 90 minus?
Theta.
Theta, that skinny triangle trick. So this is now 90 minus in here. Agreed? So actually, rather than doing it this way, I'm going to do it that way and just take that off. I know the magnitude of the magnetic torque is the magnitude of mu times the magnitude of B times sine of 90 minus theta, which is cosine. Whoa. One more time. The magnitude of the magnetic torque is the magnitude of mu times the magnitude of B external times sine of the angle between, but sine of 90 minus theta. What do you think? I guess I am helping you. My bad. I started doing too much. But I don't know. Is this helping or are we, I don't know, whatever. Hopefully there's some learning going on. Before we get ahead of ourselves, wait a minute. I want to double check something. What do we know about mu and B? What do they like to do if possible?
Align.
So if they try to align, which way is easier for them to align? Mu going this direction or mu going that way? Oh, shit.
Clockwise.
I think so. And so doesn't that make sense that this thing would try to roll up the plane? This confirms. Yeah. All right, cool. Yep. So it's going to go that way, not this way. Okay, cool. That's looking good. How do I get the torque due to mg? Where's the pivot?
The center of the circle.
Okay. Ooh, if the center's the pivot, what's the torque for mg?
There isn't one?
Yeah. So, oh my gosh. Okay, so that means maybe that frictional force isn't negligible. Do you agree? So here's the idea. There's actually an mg right here. There's a so this is mg. There's a normal force down here. And then which way would friction have to point? Let's see.
Down up the plane, sorry.
I'm going to try it. If it points this way, that would cause a torque this way, which is down the plane, right? So that would actually work out. So yeah. Evidently that friction isn't good. Now this one is so difficult to draw. I actually have it pre-drawn. So if you were looking at the solutions, you probably already saw that friction was in there. Let's go take a look.
Would it be possible to do the instantaneous pivot for this problem or no?
And so that's what I was going to ask you about actually at some point. So you could say you could do the instantaneous pivot, but the problem is the torque due to the magnetic field is not done about the instantaneous pivot, right?
Okay, I was gonna, yeah.
So you'd have to think about some kind of weird torque equivalent of the parallel axis theorem, which we don't know. So the instantaneous pivot is great for what type of trick? For what type of problem do we use instantaneous pivot?
Rolling motion?
Yeah, and this one, it's not actually rolling. It's the problem indicates that it's going to roll, but then says it stays at rest. So it's a very sneaky problem where this is not a good one to use the instantaneous pivot. All right, let's go take a look. Maybe there's a way to do that, but I'd have to think really hard. So let's go take a look at, we already did that one. All right, and so there we go. We kind of talked about that. And so there's the free body diagram. And so in this case, all right, there's a bunch of words there. I don't know. Let me pause and see if there's any questions here. You guys know how to read, but so in this case, it was the frictional force that's balancing it. We thought we could use the mg torque, but it turns out we're going to have to figure out the frictional torque by relating it to, we're going to have to do a free body diagram, right, to figure out that F has got to be mg sine theta if it's balanced. So in equilibrium both. So this one is a full-on chapter 12 problem where it balances out.
And we would know that because we know that the mg, like in your diagram, only acts at the center. So therefore
Exactly.
there's no quote unquote like lever arm
Yes.
for torque to be applied.
Yes.
Gotcha. That makes sense.
And so, oh my gosh, we could see that, oh my gosh, we're back to full-on chapter 12 hell.
Further up there, that first line that's showing, there's not a negative I-hat in there. Did that drop out earlier?
Oh, no, I think I just wrote it wrong. And then I didn't notice it because I switched to magnitudes. Does everybody agree I made a mistake here? I drew it negative I-hat, but I wrote it positive. I said, I don't know. I just screwed up. So let me write that down. What is this one? 28.20. Let me write that on this paper here.
Hey, I caught my first one.
Sweet. Fix 28.20 minus I-hat for mu. Got it. Yeah, I probably just didn't notice because the rest of it all there. This also was from an old test. I wonder if I had one of them had a south pole on top, which would have flipped it. And so maybe I had a cut and paste error too. I don't know. Yeah, that's a cool problem. All right. And so from there, I think you could do, that was a test level problem too. So I think it was Corey that said it best. There's a lot of spatial reasoning, and notice it's a throwback to chapter 12. A lot of your chapter 12 equilibrium with torques and forces come into play. Sometimes we need only torques. Sometimes forces will get the job done. Sometimes you need both. And so an understanding, so on these problems, when you're practicing them, if I explain it both ways with forces and torques, I would recommend kind of making sure you at least read it and work through it and understand both methods and try them both. Let's leave it at that for now. I don't know. What do you think? Sneaky. Fun. All right, so I'll fix that up. Let's just do a quick, before we take our break and finish strong. Ooh, look at this. This one's kind of fun. Let's have the fun. As the coil warms up, what's going to happen?
My intuition is that it would roll down.
Why?
It would be a weaker interaction.
Okay. Why would it be a weaker interaction? You haven't said anything incorrect yet.
The resistance increases and the
That's what I'm looking for.
increases.
Well, wait, doesn't the area get bigger too?
It's negligible compared to that.
Exactly.
current
Excellent.
decreasing.
So resistance should go up, but the area should go up, but resistance goes up by a dramatic amount and the area goes up by a negligible amount. So the resistance increases, current drops, mu gets smaller, magnetic torque decreases. Nice, nice. All right. Let's take a look what else we got in here. Woo, that's a good one. All right. So in the real world, permanent magnets have fields that look like this, where the field gets warped. So if I could, most real magnets, the field starts to go like this, out of north and into south. And it's going to warp around, just like an electric dipole. The field lines for a magnetic dipole are very similar, right? Imagine if you had a plus charge here and a minus charge here. Give me a sec. You know that the electric field would go out of plus, around it, and into minus. Out of plus, around it, and into minus. Same thing with north and south. So you could think of north as like a plus. Obviously, in between here, the field points this way. So in between on this magnet, this gets trickier. Well, there's a difference here. So this one's going to point up, and this one's going to point up. And one way to think about that is inside of this magnet, you have a whole bunch of circular current loops that have magnetic moments. So inside of there, you have a whole bunch of mu's pointing up. So this is one way the electric dipole differs from the magnetic dipole. Outside, they look pretty much the same, but inside, the field is going the same direction there inside the mag. I don't know, maybe that, I guess that is kind of the same, isn't it? I don't know. It looks like it goes from south to north when you're inside the magnet. Whereas when you're inside the electric dipole, it goes from plus to minus still. So there is a little bit of a difference there. All right. That said, you could do this integration and figure that out. And then this one, and I think that's the chapter, and this is a good time for a break. So I probably missed a problem or two in there, so make sure you finish up all of those. This is not easy stuff. Let's take a quick break, and then we'll come back, and we'll start with the Biot-Savart Law. I don't know what that is. Probably a piece of pizza from earlier. That's awesome. Okay. Let's just say 8 minutes or something, or let's just start up again at 6. Does anybody ever actually look at the live streams, or is it just sitting out there wasting space?
I do when I'm reviewing.
Okay.
Frequently.
So have they been good enough to be usable?
Yeah.
All right. Okay, cool. I was just curious.
So
I had a
those
student.
lives,
Oh, go ahead.
They're saved to YouTube after they're ended.
Say again. I couldn't hear you.
Those YouTubes, they are posted and like saved. We can look at them.
Yeah,
later.
they're archived. Does anybody know how to get to those? You probably, I could go look it up, but if anybody knows the link to find them, I think I put it in the Canvas modules at one time. If you have it, throw it in the chat. Okay. I wish, I had more time so I could go in and edit them and make them, split them into problems or something. Wouldn't that be nice? But I just don't have that kind of time. Gosh, I spent all day working on something that was for you guys, and it was not what I meant to work on for you guys. So I'm like, so super stressed right now.
It sounds like you need an intern.
Yeah, totally. Unpaid intern, shitty physics job. Oh man, that would just make more work, right? Oh, there you go. So, oh, nice. There you go. Yeah, he spoke up, right? Isn't that like volunteering? Is that when everybody else takes a step back?
Oh, just a suggestion. I got my projects.
Yep. All right. So before I forget, I'm not going to be in office hours tomorrow. I think I already sent you an email, but I'll do double office hours the next week. What was I going to say? I don't know. Oh, I sent you a list of project ideas for the online version of our oral presentations. They've got to be different than what we've been doing, because in class we had it was a different situation. So maybe I sent those to you, and if you want, I don't want to get an email from every single student in the class. That would kill me. So if you have one member in your group and you want to pick out your top 3 choices and send those to me, I can try to see if you get what you want. And there's enough, I think, for 2 copies of each lab. So, or maybe I'll even do 3. I think I could do actually, I might even be able to do 4 copies of each lab, because I could do 2 in the early section and 2 in the later section. And then we might split the lab presentations into 4 blocks. So there'll be an hour and a half where people are doing the first group, and then I don't know, but I have to figure all that out. But so if you want to take time right now to talk with your lab partners and figure that out while we're all together and chat and send me an email, or if you want to do it after class, there's a good chance you'll get your top pick or even your second or third. But give me your top 3 choices, and only one of you send me the email. Now, I know there's some of you, I think it might have been Corey that was looking as lab partner. He needs the new email for Wilfredo. If Wilfredo, was that right, Corey? I'm trying to remember. Okay, cool. Sorry. So awesome that you took care of that. And then there's a couple other people that might be dropping. And so I got some emails today. I'll try and look at that again. And basically, next week during lab, make sure you show up on time to the start of your section so we can try and get that done. And I know there's a couple of weird people, like Joy has a weird situation, because Joy, you're with a group and you're I forget who that was, if that was Aleda and Claudia, or if that was Anna and somebody else, Vanessa maybe. Anyways, yeah. So I realized that there's a few people that have mixed groups from early and late section, and we discussed that on a one-on-one basis. But in general, make sure you're there at the start of lab, and that way, any of these last-minute issues, we can make sure you get your right videos and stuff. That said, if you have time to send me your emails tonight, I could try to assign the groups tomorrow morning. That way, if you want to watch the videos and acquire the data in advance, I could try and do that. So the sooner you get me that information, the better. So try to get that to me tonight, your top 3 picks. Okay, if you could do that, that would really help out you. All right. And then if it doesn't come in tonight, I probably won't have time to get to it until Monday. But that's still at least a day in advance. So, all right. Okay. So that's good. Let's go on to the next chapter now, shall we? Oh. So we'll just try to move ahead a little bit in the book. There we go. Whoops. So I wasn't sure if it's legal for me to share a spreadsheet with all of the names. Oh, I see what yeah. So I'm kind of like, I don't know if I want to do that, just because I don't know if I'm supposed to be giving out other people's personal information, and even the fact of their name in the class. So that's why I haven't done this online already, Corey. So I agree, you're probably right, but some people, they have a greater need for privacy than others. So for weird reasons, and let's just, great idea. I'm worried about that, and I don't want to get in trouble. So I'd rather take the extra work and deal with it. So thanks for the suggestion. All right. Okay. Whoops. Good thought. Okay. So here's the big deal right here. All right. Remember when we had electric fields? Charges felt electric fields, but charges also created them, right? So similarly, moving charges create magnetic fields. And so because moving charge is a current, I want you to think about it like this. Currents cause magnetic fields. Currents feel magnetic force. So just like we said here, I'll just point this out. For electricity, you could have a point charge here, and the electric field, well, let's just do it like this. The electric field was K Q over R squared in the R hat. Now you could put another charge there at this spot, say Q prime, a different charge, and then we'd say, oh, well, the force felt by Q prime, so on Q prime, was equal to Q prime times that electric field. So charge was the source of the force on another charge. Okay, that's cool. Similarly, currents exert forces on other currents, moving charges, and that happens through the magnetic field. So the idea is, well, we already did this. We know that force is QV cross B, which was the same thing as IL cross B, and this is external. What I'm telling you now is B external, every external magnetic field is caused by current. And the equation that governs that relationship is total BS. It's total BS. Biot-Savart. Okay, so the Biot-Savart law is a lot like Coulomb's law for magnetism. It says that the B field created by a current is mu naught I over 4 pi. So I remember that because it kind of rhymes. Mu naught I over 4 pi times the integral of ds cross R vector over R cubed. Now you could also do R hat over R squared again. So maybe I should start with that. R hat over R squared. If you remember, what does the R vector mean? So actually, I like this R cubed. I'm going to go back to it. Sorry. That way I've got the R vector to talk about. What does this R vector mean physically in a field problem? From what to what?
From source to point.
From source to POI. And so now what's happening is, let's say you have a crazy looking wire and you run current in it. So there's current. Oh, I guess I used capital I, my bad. Doesn't really matter. The idea is if I'm sitting out here at some point, this is my source. That would be my R vector. This would be my point of interest or the point P. And so where is the B field at this point? Well, or sorry, excuse me. What is the B field at this point? Well, what I would do is I would say, take each little segment of wire. This is I times ds here. The current is a constant and factors out. ds is like the length of this little segment of wire. So if you know the length of the segment of wire in the direction current flows, that gives you all these pieces. And then you could add it up for all of these different terms here. And you could just keep adding up all of these different currents. That's the integral. And so you would get a contribution from this term, a contribution from that term, a contribution from et cetera, et cetera, et cetera. And you add them all up with the integral. That's how you get the magnetic field over here at this point of interest. Now, there's a trick we can use for figuring out just the direction. Grab that wire. Grab that wire. Don't change that dial. Okay, so in this case, if you grab the wire, notice I'm lining up my thumb in the direction of the current. And notice my fingers point out of the page. So if I grab that wire, I notice my finger, if I grab the wire in such a manner that my thumb lines up with the current. So grab that wire with thumb and current. My fingers tell me which way the B field points out of the page. Isn't that cool? And I could get that regardless of this weird ass shape of this wire. So I can get the direction of B by grab that wire. All right.
It's only because the current's moving left to right, isn't it?
It would be true if it was going this way too. Woo-hoo. Think, grab that wire, because wouldn't current keep going this way? Does that make sense?
Why couldn't you grab the wire on top?
You could.
As long as the thumb is pointed towards current.
As long as thumb points in direction of current, you're good to go.
So then, but if the thumb, wait, so if thumb's pointing in, but wouldn't it always come towards you then?
No. What if current was flowing the other way? Let me show you another trick. How about if I do this? So we could go here, and let's say I start, oh, whoops. Shit, sorry, my bad. Let's say I have this weird wire. All right, it doesn't matter. Let's say current's coming in here, okay? It's gonna come in here. It's gonna go around this way. Oh my gosh, this is getting tricky. So what if you have a coil that's all messed up like this? Then it gets complicated, right? And I know this seems crazy, but this actually relates to your homework. So not this particular shape, which is really frickin' impossible. But the idea is, if you have a wire that does all these crazy turns, what you can do is you can split it up into segments. And the idea is, on this segment, the B field up here is out of the page, right? Grab that wire. In here, into. Now, let's say that's the blue segment, just so I can keep track of it. Now, what about this green segment? Sorry, it's not very good there. Oh my gosh. So that green segment's kind of a weird, almost circle. Do you see that? So the green segment, just to outline it in case the color's not showing up, that's this one. Well, let's look at it. Right here, it points into, right?
Page.
Always into on the inside. Take a guess which way it points on the outside.
Out of the page then.
Out. Oh my gosh. Whew. So notice in this region, oh shoot, look at this. Inside of here, it's an X because it's inside the loop. So in here, they would tend to cancel. Out here, they would tend to combine. Out here, they would tend, oh my gosh. Don't you love it? Now, this is an insane example, but the point is, there was a question asked, will it always be into or out of? And the idea is, on one side of the loop, it'll either be into or out of, and on the other side, it'll be the other way. Now, same thing with straight wires. On one side of the wire, it's always going to be, in this case, on this side of the wire, it's always out of, and there it's always into. But what we see is, depending how you wire a circuit, you could actually have some places where the fields combine into, some places where they combine out of, some places where the straight portion is into and the coil is out of, and then the other side they flip. Every possible scenario is possible. Is that what that was Travis's question, I think, right?
Yeah, it just seemed like, I mean, I'm tired. I mean, we're all tired, but, I was just looking at it and I was like, working my right hand, and I was like, I cannot figure out, like, it seemed like my hand always, like, even if I flip the current, it seemed like my hand still, I don't know, faced that same way, but.
And so the idea is, it would be true. So if you're always looking at points inside the loop, you're right. If you're looking at points outside, it would flip.
Yeah, that's what I was doing wrong. Yeah.
Okay. Now there's actually another right-hand rule. Go figure. We already know it. Let's say current's flowing this way. What direction is the magnetic moment for this loop? It's supposed to be connected, sorry.
Out of the page.
So what, if you had to guess, mu represents, it relates to the magnetic field produced by this. So take a guess, what direction is the B field at the center of this coil? Out of the page. So now that you know this is the B field, what direction is the B field outside of the loop?
Into the page.
Where is the magnetic field going to be strongest? Near the wire or near the center? What does your gut tell you?
The center.
Good guess. Based on what I just said, the answer is near the wire. Close to the source, right? Now here's the issue. The field at the center of the loop is most usable in practical experience because it's roughly constant in value. It's uniform in size near the center. However, It's strongest right near the wire because you're right next to the source. Remember, the equation is to figure out B, mu naught I over 4 pi times the integral of ds cross r vector over r cubed or r hat over r squared. The idea is the closer you get to the current, the smaller r vector is. That's going to blow up huge, right? So similarly, just like if you're close to a point charge, the electric field gets huge. If you're close to an electric field source, the electric field is huge. If you're close to a magnetic field source, the magnetic field is huge. All right. Now, let's see where I want to go with this.
Just a quick tangent. You could,
Yeah.
I guess, do you think you could use graph theory to model this behavior or predict what direction
I have no
forces
idea.
would be pointing? Because I was looking into that when I went through an independent study project with Youngblood, but it's not something I've really been able to find a good use for so far.
Yeah, yeah. So that is not something I know off the top of my head at all. So you could probably ask Youngblood, just send him an email and ask. So yeah, I'll leave it at that. I don't know.
Thank you.
I have no idea. I have to look it up and do some research. So that's a good question. Good stuff. All right. Let's see. Have we covered this one? Okay. For the center of the coil, that's the one I just told you about. And for the straight wire, grab that wire. So we've talked about the right-hand rules. That's going to come in handy. So now, how do you do this Biot-Savart law? I was looking at this one, and I think I probably could have done this better. I think I could have numbered these right there. Bullets 8, 9, and 10 should really go right after 6. And then this, bullet 7, you could call this the shortcut. So the idea is bullets 1 through 6 plus 8, 9, and 10 are the full method. Bullet 7 by itself is the shortcut. Does that make sense, everybody? So I apologize. I just missed a cut and paste. So bullet 7 is the shortcut. Now, this is not going to make a lot of sense until we do a problem. So just know that this is there. I'm going to look at the problem at the bottom of the page and walk through this, okay? So this is on page 152. So I'm on page 152, and I want to look at this problem and work this one out. So I'm just going to draw this and make it look right. I'm just drawing it up still. I would draw this big. It's probably too late for me to say that. I'm sorry. You could just doodle on your workbook itself, right? That's what it's for. Okay, so we've got this crazy looking picture here. The idea is we're distance A along the perpendicular bisector. Whoa. Let's make sure everybody knows what a perpendicular bisector is. Let's say I have some random line here. Well, and let's say I want to look at this point right here. The perpendicular bisector means go from this point to the line and form a right angle. It does not mean cut the line in half. It means form a right angle like this. That's what I mean by perpendicular bisector. This line will intersect, the dotted line intersects the solid line and forms a right angle. That's what a perpendicular bisector is. So I would like to point out, I want to figure out the magnetic field at this point P. The first step is find the perpendicular bisector and draw it. So notice this is my perpendicular bisector right here. I'll make that thicker dash. So that kind of thick dashed line there is the perpendicular bisector. All right. Part B, let's see. Put a coordinate system with the origin at the point where this, okay, so this is now my origin if I'm following this step. So that's going to be my origin right there. All right. Draw ds. Well, so this is the current. I'll just put ds right next to it. Okay, so let's assume that is my little ds. IDS kind of go together. Next, what do I want to do? Label the displacement vector. All right. Now, which way do we go in general? If we're doing a field, do we go from source to POI or POI to source?
Source to POI.
Mm-hmm. So this is my R vector. Notice it's not from the left end, it's not from the right end, it's from some arbitrary point on the wire, usually in the positive axis if you can do it. Okay. Where do I go next? We've done that. So we're on step 4. We've labeled the displacement vector. Okay, so now it says figure out R. Hopefully this is sounding pretty familiar. What is the R vector? Give me an equation for it. By that, I mean how much I hat, how much J hat shit.
Minus X I hat.
Nice. We've got to make up a new term called X, right? That's over a distance X, isn't it? And then keep going.
Minus Y J hat. Or right now it would just be minus A.
Yeah, A is what we called. Yeah, that's how far it is. Is that going to be, now, do you agree I could change the value of X and that would give me each different segment of wire here? So what's R?
X squared plus A squared.
Does this sound familiar? It better. Oh my gosh, what an ugly mess.
It looks like an integral table.
It also looks like which chapter of this book that we've already been doing?
It's like the beginning chapters, right?
Chapter 22, continuous distributions of charge. There, now here's why we spent so much time on that. When we were doing electric fields and I made you do all that stupid shit in coding and stuff, we're trying to figure out how this happens when you add up a bunch of charges. Well, now that we're in current land, we don't have a choice. Currents are always distributed over a wire. So we have to do these integrals to understand current. There's no trick. We can't just say a point current. That doesn't exist. So we have to do these integrals, and hopefully you're like, wait a minute, hopefully this is quicker to learn now because I punished you severely in chapter 22. That was the goal. I hope it worked. Anyways, all right. So we've got all our pieces, plug it in and do some stuff, right? Is that the next one? Shove it in. All right, so let's go. Now I'm just going to go this way. I know that I don't really need the R hat, so let's just do it this way. Mu naught is some constant. Oh gosh, I forgot. I said this yesterday, but not everybody was there yesterday. Mu naught is just some constant. Sorry about that. It's 4 pi times 10 to the -7, and then there's some units. We'll figure out the units after we do the formula, okay? So let's write down the formula. So it's mu naught I over 4 pi times the integral of ds All right, so let's do a quick check. Let's get the units of mu. I forgot. What are the units of B? Oh.
Tesla.
Tesla. Okay, so what are the units of I? That's an amp. And then we've got the units of mu, naught. What are the units of that garbage? 4 pi has no units. What are the units of this?
1/meters.
So I got a meter, and then I got meters cubed. So meter squared, did you say 1/meter?
Yeah.
I think you got it. So notice, what are the units of mu naught? Tesla meter per amp. Who cares? We'll worry about that later. Sorry, I forgot to say that earlier. My bad. I'm tired too. You guys are. 4 minutes to go. 4 minutes to freedom. All right. At this point, what is ds?
dx.
What is it again? I couldn't hear you.
dx.
Not quite. That's part of it.
I hat.
I had, because it was a vector, right? All right. So remember, it flows in the direction of current flow. All right. Oh my gosh. This looks like it's going to be a nightmare, doesn't it? Or does it? Maybe it's only a mildly bad dream. Because it's to the 1/2 and then we cube it, I get a 3/2. What's the first thing you do when you have an integral with a cross product inside? What's the first thing?
You do the cross product.
You do the cross product. Here's one big reason why. How does this simplify?
The eyes cancel.
Eyes. The I, matey. I hat cross I hat. Disappears. I hat cross I hat is 0. What's I hat cross J hat?
K hat.
And then we got a minus. So I think this becomes minus a K hat. Is that right? Well, I just erased it. That wasn't very smart. I have no idea what I wrote. But is that right, everybody? I think that's what we said, right? Whatever. Now, wait a minute. Look at this. Constant, constant, constant factors out. It's really just dx over that. Man, that looks like a tough integral, doesn't it? Integral table. There it is right there. So you get some stuff, you do some things, and you figure some stuff out.